and y. Linear programming problem in X and Y consists of optimizing. Optimizing means that you're either going to maximize or minimize a linear function, say like z equaling ax plus by, where a is some real number, b is some real number, and you don't want that well, if you want in two variables, then you don't, this is called an objective function. Actually, I could have that at 0. It'll just be a really easy problem. So this is called the objective function, and it's subject to certain conditions. These conditions are called constraints. These constraints are expressible as linear inequalities in X and Y. The region in the plane satisfying constraints is called the feasibility region. A point in the feasibility region is called a solution to the linear programming problem consists of a feasible point that optimizes the objective function together with the corresponding value of the objective function. If a linear programming problem has a solution, then is located on a vertex of the simplex, on a corner point, region. The feasibility region, since it consists of a whole bunch of linear inequalities, it'll be called a simplex. It's just some sort of linear polytope. If a linear programming problem has multiple solutions, then at least one of them is located at a corner point of the feasibility region, at one of these vertices. If you have multiple points, you'll actually, if you have more than one solution, it'll actually lie along one of the sides, of the feasibility region. In either case, the corresponding value of the objective function is unique. So even if you happen to have more than one value that optimizes it, the actual optimal value is unique. So for example, suppose we have p equaling 3x plus 7y. This is called the objective function. And suppose, I don't know, we want to optimize it. So suppose we want to maximize p. So this is why it's called an objective function, because that's your objective. Your objective in the problem is to maximize, and it's subject to some constraints. So not all values of x and y are admissible solutions to the problem. Suppose we have something like x is greater than or equal to 0, y greater than or equal to 0, x plus y less than or equal to 20. This is, these would be considered your constraints. Notice they consist of a whole bunch of linear inequalities. So things that we did in the very last section. A convex polytope. So these will give us a convex polytope, some sort of simplex. So for example, this region here, that I guess maybe I'll so this is this is my feasibility region. So the thing that I've just shaded here is my feasibility region. These this feasibility region satisfies all of your constraints. So suppose you had a whole bunch of constraints and they all were satisfied giving something that looks something like this. These corner points are called vertices. We then look at the value of your objective function. Say your objective function is some linear objective, in which case it'll just look like some line, and you'll figure out the value of your function along the line. And it will turn out that, well, it will be optimized along, well, if you look here, well, the smallest values here at this point, biggest values over here. Now, it could be that your line is such that it sort of intersects here, connecting two of these vertices, in which case the optimal solution will be along this whole line here, along one of these sides of your simplex. So let's do some examples. On page 639, maximize P subject to the following constraints. Problem number 12. P is equal to x minus y. That's your objective function. You're subject to a whole bunch of constraints. 5x plus 4y less than or equal to 20, y less than or equal to 5, x greater than or equal to 0, y greater than or equal to 0. Okay, so let's first try to draw the feasibility region. So let's determine the feasibility region. So, well, I have here 5x plus 4y less than or equal to 20. Let's try to write that in standard form. So let's subtract 5x from both sides of my equation, of my inequality. And then let's divide both sides of my inequality by 4. So y is less than or equal to negative 5/4 x plus 5. So in this case, this is going to be true.
Professor, I have a question. How
Sure.
did you get 20?
Right there. That's
okay, I missed that.
that's what the that's the constraint. So it was given in the problem. So that particular equation was given, or inequality was given in the problem, and so it's a constraint. Okay.
Oh, so we don't use the objective then? We just use the constraint? Because I was using it for the objective.
Okay. Yeah. I didn't quite hear what you said. You're a little bit too low.
Oh, I said that I was using the objective.
Oh, we're right. Right. No. Just so right now I'm going to do the feasibility region. So first I'm going to draw the feasibility region. I'm going to first draw this, and then I'll find the value of my objective function along, well, at each of these corner points, at each of the vertices of the simplex. Okay?
Okay.
So first I don't care about the objective yet. So I'm
okay.
just doing the feasibility region. So this is true below. It's also going to be solid. I hope these are all solid. If not, these are all going to be For these linear programming problems, they'll always be equals. Okay. So the slope is minus 5/4, and the y-intercept is 5. So the y-intercept here is 5. Okay. Next, we have here y is less than or equal to 5. Well, maybe I won't even, well, I will say what they are. So y is less than or equal to 5. So this is going to be true below. And this is going to be solid. They're all going to be solid. I have here x greater than or equal to 0. So again, this is true to the right. And again, it'll be a solid line, solid boundary line. And lastly, I have here y is greater than or equal to 0. So this is going to be true above. And it'll be a solid line. Okay, so now let's draw the constraint. Okay. Let's put tick marks. I noticed that this is going to be in the first quadrant. So that's why I drew mostly the first quadrant. That's where the feasibility region will occur. Okay, so I have that x is equal to 0. That's just this line. And it has to be true to the right. So it's in this region here. Y is greater than or equal to 0. So that's this. It's going to be, and it's greater than or equal to, so it's true here. I think also y was less than 5. Let's equal to 5. So 1, 2, 3, 4, 5. Well, even though it's not, it should be solid. Let me draw it. Actually, I'll draw it solid, but not in, I'll draw it in red. 1, 2, 3, 4, 5. And you'll see in 1 second why I'm going to do that. Okay, so it's below. Basically because it won't make any difference. This line actually doesn't do too much. Okay, and then the other one had a, now I forgot, a slope, so it went through 5 and had a slope of negative 5/4. So it went through 5, that's why I didn't care, and it has slope of 5/4. So it should look like that's a 4. That's a 4 right there. Okay, let's see if I can do it. 4 and a 5. Okay. Okay. As good as I can do. And it's true below. So if I do that, I see that my feasibility region, that's why I didn't want to draw this too solid, is just this region here. And so it's going to look something like this. So it sort of went over, but okay. There. And so here's my feasibility region. Okay, so if I look here, well, if I try to optimize it so you'd have some sort of line going across it, well, it's going to be maximum either this point, or this point, these vertices, or maybe possibly along one or two of the points. So let's look at these 3 points. Let me actually, maybe I'll say what they are. This is going to be 0, 5. This is 0, 0. And this is 4, 0. So there's really 4 numbers I have to look at. Okay. So let's determine the value, determine VP at each of these corner points, at each vertex. Okay, so let's find the value P at the origin. Well, this is just 0 minus 0. And so this is just going to have a value of 0. Okay. Next, let's figure out the value at 4, 0. That's just going to be 4 minus 0. So 4. And lastly, let's figure out the value at 0, 5. So this is just negative 5. So now that I've done this, I want to optimize P. So let's determine the optimal value. So if I look here, I want to maximize P. So the maximum of P is 4. So I only had 3 numbers to look at, 0, 4, and negative 5. Well, the biggest of those numbers is 4, and it occurs well, it occurs when x is 4 and y is 0. And that's your answer. And so that's the idea of linear programming, is just to determine your feasibility region, and then find what the optimal value is. In later courses, you'll actually find there'll be a technique which will be very similar to the technique that we use for Gaussian elimination, this sort of pivoting idea. that it's called the simplex method, where you can very efficiently determine the optimal value, and you will not need to graph the this sort of picture. You would just traverse the from one vertex to the next, going in the direction where it optimizes your function, your objective function. Okay, but we're not going to do that in this course. Okay, so let's determine the feasibility region for this. So minimize P subject to the following constraints. So problem number 20, I want to minimize P equaling y minus 2x, subject to x plus 2y less than or equal to 4, 2x plus y less than or equal to 4, x plus 2y greater than or equal to 2, 2x plus y greater than or equal to 2. So if you notice, we really only have two differing inequalities. Really, this says that x plus 2y is between 2 and 4, and this says that 2x plus y is between 2 and 4. So I'm really going to only just look at two of them. So determine the feasibility region. Okay, so I have here x plus 2y is less than or equal to 4. So solve for y. So I have 2y less than or equal to negative x plus 4 divided by 2. So I have that y is less than or equal to. Okay. So again, as always, it'll be solid. And this will be true below. Okay. The slope, negative 1/2, and the y-intercept, the y-intercept, there it is, of 2. Well, in addition, I had x plus 2y was greater than or equal to 2. So doing the same thing, I see that y is greater than or equal to negative 1/2 x, because the coefficient in front of x is the same. Here, we're going to, instead of dividing 4 divided by 2 to get 2, I'll divide 2 divided by 2 to get 1. And so I have that this is going to be true below, true above, sorry, true above, of course, solid. It's going to be parallel. So the slope, and I think this is the third one, third equation, is negative 1/2, and the y-intercept is 1. Okay, so there'll be two parallel lines, just a distance of 1 apart. Now let's look at the other one. And so the other one was 2x plus y less than or equal to 4. There. Less than or equal to 4. Subtract 2x from both sides, so y is less than or equal to negative 2x plus 4. And so again, this is going to be true below. And as always, it's a solid line. If it wasn't if it wasn't solid, then that means you would not include that side in the feasibility region. So it would actually sort of mess up a lot of things I was saying about the fact that they would occur, the optimization would occur at one of the corner points at one of the vertices. So they're always equal signs. The constraints always have an equal in them. Okay, so the slope in this case is -2, and the y-intercept is 4. And then the other one is the same, but it had a 2 in it. So 2x plus y greater than or equal to 2. So that says that y is greater than or equal to -2x plus 2. So again, this is solid. True above. The slope is -2, just like before, but the y-intercept is different. It's 2. Okay, so now let's draw the region, the feasibility region. Okay, let's put all my tick marks. So now that I have my tick marks, I had a 2 and a, let's see, I had a 1 in it. A 1 and a 2. Okay, so for this one, it was a 1 and 2 and slope of -0.5. Okay, so there's a 1 here and a 2. I should make these a little bigger, maybe. Actually, that's, so these tick marks are at 1/2. So at 1 and at 2, and the slope is -0.5. So you go over 2 down 1, over 2 down 1, over 2 down 1. Okay, so it looks something like this. And this. It's supposed to be parallel. Obviously, I missed that. Okay, better. Okay, so, and this was in this direction, that direction. Okay, and then the other one was, oh, 2 and, oh, was 1 and 2. So it's 4. 3, 4. Okay. These are halves, I remember. Okay, I made them bigger. Okay, so at 2, oh, maybe I should have made it that way, because at 4, it's going to be way up here. Okay. Sorry. I shouldn't have made it so big. Let me just get rid of this for 1 second. I'll keep it where it's a unit, where these are just units. So 1, 2, 3, 4. They all have negative slopes. Okay, so I'll just draw this one first. So 1, 2, and I have a slope of -2. So over 1, down 2. Okay, so that'll be this one. And it's true above. Okay. Next, at 4. 1, 2, 3, 4. Okay. And parallel, so it goes like that. Okay. Okay. Next, that's a 4. Okay. And then let's do the first two. And so this was at 2, it has a slope of -0.5. So at 2, oops, at 2, at 2 has a slope of -0.5. So it goes over 2, down 1. So it has to look something like this. Just like that. Okay. Next, we have, it goes at 1. Oh, the next will be at 1. Okay, so it looks like this. Okay, that's at 1 there. Okay, so this goes like this. So the feasibility region will actually just be this little region here. So this is my feasibility region. Okay, and so here are the 4. There are 4 vertices. Okay, and so let's figure out what each of those vertices are. So let's determine the vertices. Once I've determined the vertices, then I can figure out what the value of the objective function each of these vertices are. Oh, and maybe what I'll do, just to make my life easier, so this is minus 2x. So this was the equation y equals minus 2x plus 4, y equaling minus 2x plus 2. That was these boundary lines. And then the other was y equal negative a half plus 1, y equal negative 1/2 x plus 2. Okay, so let's try to determine where these two intersect. Well, that's when these two lines are equal. And so let's try to determine when minus 2x plus 2 is equal to minus 1/2 x plus 2. So I'm just going to set those two equal to each other and see what happens. Well, we can actually see it's going to be at 0, 2. And so the 2's cancel. And so I have here that minus 1/2 x, minus 2x, I'm sorry, is equal to minus 1/2 x multiplied by negative 2. So I have 4x is equal to x, subtract 1 from both sides, 1x. So x is 0. But if x is 0, then I have that y is equal to, well, it doesn't matter which one I use, say negative 2x plus 2 is 2. So one of the vertices is at 0, 2. So that's one of the vertices, which we could see was fairly obvious that this was at 0, 2. Let's look at the other ones, which aren't going to be quite as obvious. So let's set negative 2x plus 4 let's see when that's equal to. So when this negative 2x plus 4 is equal to the negative 1/2 x plus 2. Let's multiply by negative 2 to get rid of all these. And so this is equal to 4x minus 8 equals x minus 4. Subtract x, add 8 to both sides of your equation. So x is equal to 4/3. Okay. Let's find the corresponding y value. So y is equal to negative 2 x plus 4. So y is equal to negative 8/3 plus 4. I can write that as 12/3. So y is equal to 4/3. Therefore, another vertex is at 4/3, 4/3. And so that's another vertex is here at 4/3. 4/3. Let's figure out maybe where this one is. When the minus 2x plus 4 is equal to the minus 1/2 x plus 1. multiply by -2 to get rid of the negatives and the fractions. So I get 4x minus 8 is equal to x minus 2. Subtract x, so 3x is equal to 8 minus 6. 8 minus 2 is 6. So x is equal to 2. Okay, good. And let's figure out what y is. So y is equal to a negative 2x plus 4. So y equals 0. And so we're at 2, 0. So your other vertex here is at 2, 0. Okay. And let's look where this vertex is. So negative 2x plus 2 and I want to set that equal to negative 1/2 x plus 1. Set those equal and see where these intersect. Let's multiply by negative 2 to get rid of the fractions and the negatives. So I get 4x minus 4 is equal to x minus 2. Subtract x from both sides. Add 4 to both sides. So x is equal to 2/3. And let's figure out y. So y is equal to negative 2x plus 2. So y is equal to, where it is. So y is equal to negative 4/3 plus 2 is the same as 6/3. So y is equal to 2/3. And so another point of intersection is at 2/3, 2/3. So that's the point of intersection. Okay. There it is. So this is another point of intersection. Is at 2/3. Okay. 2/3, comma 2/3. So that's the other point of intersection. So there are these 4 points, these 4 vertices. So let's determine the value of my objective function at each of these vertices. So let's determine the value of p at each vertex, at each of these corner points. So let's determine the value of your objective function at each vertex of your simplex. So let's do this first at 2, 0. And so my objective function is y minus 2x. And so in this case, my value is negative 4. Let's figure out the value at 0, 2. So it's y minus 2x is equal to 2. And then let's look at, let's say 4/3. So the value of 4/3. And so it is y minus 2x. So 4/3 minus 8/3 is a negative 4/3. And lastly, let's look at 2/3. So the value of my objective function at 2/3. So it's y minus 2x. And so 2/3 minus 4/3 is a negative 2/3. Okay, so in this case, we wanted to minimize this. And so the minimum is negative 4/3. And so P, oh no, wait, negative 4. I'm sorry, I forgot about the first one. And so P is minimized. So P has a minimum of negative 4 at 2, 0. And that is your answer. Okay, so that finishes off section